Hello, everyone. My name is Gustavo Ramirez. I'm a mechanical engineering major, and I'm entering my fourth year this upcoming fall. I'm an undergraduate researcher at the BMEC lab under Dr. Skandari, where we look at the lung through the lens of a mechanical engineer. Today, I'll be talking about the development of a novel pulmonary healthcare device. So with every breath, your lung undergoes pressure and volume changes, constantly stretching and compressing. As a result, the structural material experiences stresses and strains. One of the things we do at the BMEC lab is we look to characterize these mechanical properties, compare the differences in these properties between a healthy and a diseased lung to gain further insight on pulmonary mechanics. I'm going to be talking to you about a new pulmonary healthcare device that I've been working on for the lab that looks to harness a new mechanical biomarker. This biomarker is the viscoelasticity of lung tissue. I'll talk a bit more about what that means later. But we intend to use this new biomarker in our device in order to detect, diagnose, and monitor a patient's progress through their pulmonary condition. I'll be sharing a bit about the background information, development, and expectations for the device. First, to start off with a little bit of background information. So pulmonary disease is a global leader in morbidity and mortality rates. If we wind the clock back to pre-pandemic times in 2019, the World Health Organization lists COPD, or chronic obstructive pulmonary disease, as the third global leader in fatality rates. Fast forward to today, of course, the world is enduring the COVID-19 pandemic, an infection that targets the respiratory system and has largely affected our day-to-day lives. Lung tissue is characterized as viscoelastic. Pulmonary diseases and infections like COPD and COVID-19 cause structural changes in the lung, specifically in the viscoelasticity of lung tissue. A viscoelastic material contains both viscous and elastic properties. You can think of the viscous aspect as honey running, and the elastic process as a rubber band being pulled and returned to its shape. Our lung experiences a combination of these properties. We're trying to harness the viscoelastic response of the lung tissue. In ex vivo experiments done at the BMEC lab, we noticed a heterogeneous strain response of the outer lung tissue when air was pumped into the lung and held there, or when a lung holds its breath. So the pressure generated within the lungs, specifically when someone is holding their breath, is a result of passive relaxation of the interior lung tissue. This relaxation is dependent on the viscoelastic state of the lung tissue. A diseased lung might experience deterioration or reinforcement of this tissue. The proposed device intends to harness this new biomarker along with a few other measurements that will help in determining a patient's respiratory condition. For development of the project, we begin with our primary component, a custom range pressure sensor. We chose our range after a quick literature search where we looked for data regarding mouth pressures on both maximum inspiratory and expiratory efforts. We found multiple studies on mouth pressures and came up with a couple of comfortable range expectations for maximum inspiratory and expiratory efforts. Inspiratory range from -0.3 to -0.17 bar, while expiratory pressures range from 0.03 bar to 0.2 bar. We chose a pressure range for our sensor of -0.25 bar to +0.25 bar to give us some wiggle room in case of any outliers. The pressure sensor is responsible for detecting the pressure drop created by a patient's lungs as they inhale and hold their breath. So the next measurement we needed was the amount of air a patient inhales during an inspiratory effort. We wanted to track this with a volumetric cylinder and a plunger that displaces inside the cylinder according to how much air the patient inhales. The figure on the right shows the different volumes associated with the lung. The volume we're most interested in is the inspiratory capacity right there, which represents the amount of air a human can inhale in a single breath, which is about 3,000 milliliters or 3 liters. We use this value to pick out a volumetric cylinder, our volumetric cylinder dimensions. We chose a cylinder with an inside diameter of about 5 3/4 of an inch and a length of 10 inches, which gives us a total volume of roughly 4 liters of air to be inhaled. And there's a little GIF of the device that we built this. The volumetric cylinder is sitting on a custom 3D printed base, and the plunger I mentioned is being displaced by, you can't really see it in this video, but there's a tubing coming out of the front and I'm inhaling through that tubing. So now that we talked about how we want to pick up the measurements, I want to show how all the pieces come together in the big picture. This is a CAD model of our design. We can start from left to right, beginning with the pressure sensor housing. It consists of 3 components. The top being the most important. It's an airtight chamber where our pressure sensor is making readings. The other 2 components shield the sensor and make the device easy to handle for our patient. On both sides, we have 1/2 inch push to connect inserts, which makes it easy to attach and detach the plastic tubing that's going to be running from our patient's mouth over to the right-hand side in the volumetric cylinder. As we head over to the volumetric cylinder, we run into a shutoff valve. Now, this is important because, as I mentioned, the first chamber needs to be airtight, and we know for a fact that our volumetric cylinder isn't airtight. So we need to be able to cut off access to the leakiness of the volumetric cylinder once our patient is done taking a breath. There we have our volumetric cylinder that I mentioned in the previous slide. The plunger is sitting on the right end of the picture near the end cap. And the volumetric cylinder is sitting on a custom 3D printed base. At the end of the custom 3D printer base, we have a ultrasonic sensor mounted. This sensor is picking up the distance that the plunger is displaced when a patient inhales. And we use the geometry of the cylinder to calculate the volume of air a patient inhales. And both the sensor, the ultrasonic sensor and the pressure sensor, are being ran through to an Arduino, which is actually housed on the other side, but for visual purposes, we'll put it there. And the Arduino is feeding data to Arduino software and MATLAB at the same time to plot our results live, which I'll show you a little bit in the next slide. So this is our current GUI. It's programmed to output and plot the sensor reading live as the patient uses the device. The graph will show a pressure versus time plot, and next to it, we have the Arduino displaying the sensor measurements for the amount of air a patient inhaled and the latest pressure value. We're currently in the stage where we're working to refine each component individually before we integrate them together. On the pressure end, we have secured an airtight chamber that is able to read the viscoelastic pressure drop. The plots shown are a pair of my trials where I took a breath at a relatively rapid rate and cut my breath off with the shutoff valve. This led to the nice curvy decline in pressure over the given period of time. So we're currently experimenting with different breathing rates and different ways to shut off the valve in order to find the method that yields the most repeatable and rewarding results. And a little bit to illustrate what's going on in this graph. So the flat horizontal line represents pressure at ATM rate, so 0. And then the initial pressure drop is, or that first spike down is the initial pressure drop created by your lungs. You can see it on both graphs. The peak is where I start to hold my breath. And after that, the lung begins to relax. As you can see, it doesn't go straight back down to atmospheric pressure. It has a slow, gradual decline. And this is what we consider the viscoelastic pressure drop. And we're hoping that it's a key teller as far as early detection in pulmonary disease. The device is currently scheduled for human clinical trials this November. If COVID regulations permit, in terms of what we expect, pictured on the right is one of the same plots from the previous slide with some annotations predicting what a diseased lung curve could look like. The thin blue line represents a healthy curve. And the red line, as you can see, has a steeper decline toward a relaxation rate. This curve might be caused by a patient with pulmonary fibrosis, which makes pulmonary lung tissue more rigid. And the green curve drops to relaxation state much faster. This might be the curve of somebody with emphysema, which deteriorates lung tissue. I want to close by not only reiterating that the device is going to harness viscoelasticity as a biomarker, but I want to highlight the differences between the proposed device and other respiratory diagnostic methods. The most common diagnostic method today is spirometry. Though this test is relatively inexpensive, the methods depend heavily on a patient's repetitive effort to inhale and exhale at a maximum rate. Our device does not rely on a patient effort for a meaningful reading. The device records the viscoelastic pressure drop as the patient holds their breath. This is a passive response out of the patient's physical control. The viscoelastic pressure drop will vary depending on the pulmonary condition of the patient. And finally, I want to conclude by acknowledging Dr. Mona Skandari for giving me the opportunity to work on this project. It's been a great experience. I also want to acknowledge Nikos, my research partner, everybody at the BMEC lab who's been a great help this summer. Of course, Nee, Tran, and Dr. Brown for opening the door to us under RISE and CAMP. Also, the peer mentors for supporting us through this program. And last but not least, the NSF for helping fund RISE and CAMP. And I open it to questions and comments.